quadratic equation. Okay, we have the standard form of ax squared plus bx plus c is equal to 0, whereupon we have the a cannot be 0. And tied in from this, if I were to express what we have in terms of the variable x, again, we have from this, we have the quadratic formula. Okay, so we have the x is equal to negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a. And again, the problems involving the quadratic equation are not necessarily limited to the variable x. Now, from what we have from the set on pages 68 and 69, okay, so we have, say, regarding number 64, and we have an equation, this time in the letter n. Okay, so we've been changing up variables like the other day, and this exercise set kind of maintains that flow. Okay, going from one letter to solve for, changing up from one to another. Okay, so we have n squared plus 8n is equal to negative 3. And so we have a quadratic equation, but we do not have it in standard form yet. Okay, so we have like replacing x with n. We have like ax squared is represented by n squared. Bx, or if you were to replace x with n, we have 8n. And we have the constant, okay, to be at 3, but this is situated on the other side. So if I rearrange the terms and set this up as a quadratic equation, okay, that is in standard form. So we have n squared plus 8n plus 3 is equal to 0. And if you notice, okay, if you were to try factoring into integer coefficients, we're not going to be able to do so. Now, we could try factoring n squared to n times n, but in the case of trying to factor 3 into items that will add up to 8, you got 3 and 1, 1 and 3, negative 3, negative 1, and so forth. And the combinations will either add up to 4 or negative 4, but not 8. Okay, so we have as a recourse, okay, if we look at setting up what we have in the quadratic formula, okay, again, so we have negative b plus or minus the square root of b squared minus 4ac and we have all over 2a. All right, and just looking at what will represent a, b, and c. Okay, so we have n squared, and you would read this as if it were 1n squared. So we have that a is equal to 1, and we have b is equal to 8, and we have that c is equal to 3. And so looking at what we have with a, b, and c and the respective values, so if we cross over to the substitution stage, we have negative b becomes negative 8, and then plus or minus, okay, and we have the square root, okay, so b squared becomes 8 squared, and we have minus 4ac, so we have minus 4 times 1 times 3, and we have all over 2a. Okay, so we have it 2 times 1. Sorry about that. Okay, and we have, okay, so we have 2 times 1 is 2, and we have negative 8 plus or minus, and we have the square root, and 8 squared, okay, 8 times 8 is 64, and being careful with the minus 4ac portion. Okay, you have negative 4 times 1 is negative 4. In turn, negative 4 times 3 is negative 12. And we have negative 8 plus or minus, okay, the square root of 52. And we have all over 2. Now we have with the square root of 52. Okay, now 52 is not a perfect square value, but it is a multiple of a perfect square that is greater than just the number 1. And now again, you have with your perfect squares, we have 1, 4, 9, 16, 25, 36, 49, 64, 81, and so on. Now into the number 52. Okay, 49 won't go into it, 36 will not, neither will 25, 16, or 9, but 4 will go into 52 13 times. So if I were to lower the square root of 52, okay, so I have 4 times 13, so if I separate, I have the square root of 4 times the square root of 13, and the square root of 4 becomes 2. And just bringing down the radical portion, okay, we have the square root of 13. And we have, in the case of the rewrite, okay, so you have negative 8 plus or minus, and for the square root of 52, okay, I have 2 times the square root of 13, and we have all over 2, and you can either separate the terms and simplify, in fact, what we can do here, yeah, we'll separate, see we have negative 8 halves, plus or minus 2 times, okay, the square root of 13, all over 2. Okay, now we have negative 8 divided by 2. Okay, that is going to be a negative 4. And for what we have with 2 times the square root of 13 over 2, okay, we get the 2's to cancel. So it'll be negative 4 plus or minus the square root of 13, and in terms of itemizing the values, okay, so we're going to have negative 4 plus the square root of 13 as well as negative 4 minus the square root of 13. Okay. All right, so you have these terms with the radical as such, and so in these now the solutions, you have negative 4 plus and negative 4 minus the square root of 13, and if you have anything with a radical of such as a square root of a term that cannot be reduced, okay, you're going to have what would be regarded as irrational roots, okay, and 64 is such a case. Now again, I had said that for equations you'll be looking at fractions time and again, and before I move on to the next item, there is a category I do want to mention, and this will be what we have in the case of proportions. And for what we have in the case of proportions, a proportion is going to be a statement of equality between ratios. And you can have like a proportion, say that if A over B is equal to C over D, then you'll have an equality between what would be regarded as proportional cross products. And what I mean by this, you're looking at multiplying alternating numerators and denominators. So in the case of A over B equal to C over D, then you're going to have that A times D, first numerator times the second denominator, is equal to what we're going to have interacting between the second numerator and the first denominator. So you have A times D is equal to C times B, or B times C, and this will be on the condition that for the proportions to be defined, neither B nor D can be 0. Again, in fractions, you cannot divide by 0. So in other words, the bottom part of the fraction cannot be 0. So this will be a general case of what we have concerning proportions. Now, an example of a proportion, if we're looking at solving for x, and we just set this up as a proportion. And let's say that if we have 2 over x plus 4 is equal to 1 over x minus 3. Alright. Okay, first of all, whatever we have for x, okay, we cannot have 0 denominator values. Okay, so whatever we have for x, you cannot have like x plus 4 to be such that we end up with 2 over 0. So you have x plus 4 cannot be 0. Okay, so we cannot have x equal to negative 4. Likewise, with the other ratio, we had that denominator cannot be 0, so x minus 3 cannot be 0. So x cannot be equal to 3. Okay, so x cannot be negative 4. And we had the x cannot be at 3. So we have those restrictions in play. Now, where the proportional cross products will come to the scene. Okay, so you have like A over B represented by 2 over x plus 4. C over D we have represented by 1 over x minus 3. Now for A times D, okay, we have mapping together. We have 2 times the quantity of x minus 3. And you have B times C or C times B. Okay, we have, in this case, we have 1 times x plus 4, which is just going to be x plus 4. And looking at distribution, we have 2 over the quantity of x minus 3. This would be 2x minus 6 is equal to x plus 4. And we're back in the terrain of whereupon we have 2 sets of like terms. Okay, one set in the variable x, the other set being constants. And if we combine the variable terms, like we have 2x to the left, x to the right, and my suggestion would be to take out the smaller variable term first. Upon doing so, the left-hand side becomes x minus 6 is equal to 4, and then getting x by itself upon adding 6 to both ends, and we're going to have an apparent solution with x equal to 10. Okay, so first of all we have x equal to 10, and this satisfies the restrictions that x cannot be negative 4 and that x cannot be 3. And you can sort of go back and check what we have for 10. You have 2 over 10 plus 4, which will be 2 over 14. Now 2 over 14 is equal to 1 over 7. Okay, so the left hand side is equal to 1/7, and to the right I have 1 over 10 minus 3, and that is also 1/7. So we have consistency with this value at x equal to 10. Yeah. And so you're going to have some proportions a bit in sync with items that could lead up to quadratic equations. Now, for what we have, just going back to our problem set, now we have for number 68, and we have here the equation we have in terms of the letter t. So right now we have 1/3 minus 4/3t is equal to 7/t. So we're looking at solving for t, and where we have t situated, we have in denominator position. Okay, so we have for 3t. Okay, first of all, 3t cannot be 0, and if 3 times t cannot be 0, well, we had that t cannot be 0. And the other existence of t, okay, well, that's just a standalone variable. Again, we have one restricted value, and it's just that t cannot be 0. Now, if we look at clearing out the fractions, and we have 3 and t, and also we have 3t, and if we convert these fractions into terms that have integer coefficients, we can multiply 1/3 -4/3t as well as 7/t by the least common denominator, and that's going to exist with what we have in the second ratio. So 3 will go into 3t, t will go into 3t, and 3t will go into itself. And looking at clearing the fractions, so if I take these terms and multiply by 3t, we say 3t minus 1/3, and just bring down the subtraction. I've got 3t times 4/3t. And we have is equal to 3t times 7/t. And I tell you what, you could do a bit of cross multiplying, but I'm just going to multiply directly. Okay, so you have 3t times 1/3, so we have 3t/3. And we got minus 3t times 4 is going to be a negative 12t over 3t, and 3t times 7 is 21t over t. And for what we have here, okay, so you got 3t/3 goes to t, negative 12t/3t, that will go to a negative 4, and 21t divided by t goes to 21. And now we have t minus 4 is equal to 21, and isolating t. Okay, so if I add 4 to both sides, okay, we're going to have an apparent solution for t, which will be at 25. We can go back and check. So 25 is non-zero in value. Again, 3t times 1/3 goes to t. Got subtraction, and 3t times 4/3t leads to the subtraction of 4. And again, with 3t times 7/t, t's cancel out, and we have 21, and 25 will check out. Now a case of what you might have, let's see, don't think it's that one. See, we have in 74. Okay, Now we got 2 over c plus 3. And we have minus 1 over c minus 3 is equal to 10 over c squared minus 9. And since I'm looking for restricted values, what I'm going to do here is that for this last ratio, I'm just going to put this in factored form. So you have 2 over c plus 3 minus 1 over c minus 3. And we have is equal to 10 over. And c squared minus 9, we have c plus 3. And c minus 3. So now we have, in the expressions, now we have 2 distinct factors, or denominator factors in c. You have c plus 3 and c minus 3. C squared minus 9 is just a repeat of c plus and c minus 3. Now for the restricted values, okay, so neither c plus 3 nor c minus 3 can be 0. And c minus 3 cannot be 0. And we have that c cannot be 3. And now, just a little bit of history repeating. Now, clearing out the fractions. Okay, we're looking at multiplying these 3 ratios by the least common denominator. And so for what we have here, we got by itself we have c plus 3. And the other denominator factor, okay, that's going to be at c minus 3. And all 3 denominators will go into this formed least common denominator. And if we look at these terms and multiply by the least common denominator, okay, so we have at the front, okay, so you have the quantity c plus 3 times c minus 3 you have times 2 over c plus 3. Okay, so if I pause, okay, look at this first term, okay, like what is happening to 2 over c plus 3 when multiplied by the least common denominator? And if you notice, okay, we have the denominator, we have at c plus 3, and multiplying by the least common denominator, we have c plus 3's are going to cancel. So that leaves us with 2 times the quantity of c minus 3. Now if I bring down the subtraction and apply the least common denominator against it, you have c plus 3 times c minus 3. And I have times 1 over c minus 3. Now what's going to happen here, okay, is that we're going to have c minus 3's are going to cancel. Okay, so we still have subtraction that will be affecting all of c plus 3. And then we have to the right, we have the quantity c plus 3 once again, times that of c minus 3. And we have times 10 over. Okay, we have the quantity of c plus 3 times c minus 3. And guess what? Both c plus 3 and c minus 3 will go out. And only 10 will be left on the right. So looking at what we have after clearing out the respective denominators from the original setup. Okay, so you have C minus 3 and 2. So just looking at applying, so you have 2 times the quantity of C minus 3. And you got subtraction. And this is going to affect all of the binomial that we have with C plus 3. Again, we have is equal to 10. Okay. Now again, C minus 3 times 2, 2 times the quantity of C minus 3. It's kind of like A times B is B times A. So just reversing the order of the factors. Now we can distribute. So you have 2 times the quantity of C minus 3. Okay, so this will be 2C minus 6. And then distributing subtraction over the quantity of C plus 3. So these terms will become negative. Think like negative 1 times C is negative C. Negative over positive 3, that will be a minus 3. And we have is equal to 10. And gathering our like terms on the left. So you have 2C minus C becomes C. Negative 6 minus 3 becomes negative 9. Again, we have C minus 9 is equal to 10. And then we have for the value of C itself, if I add 9 to both ends, we're going to have that C is equal to 19. Okay, so on the basis that we carried out the operations and working with the least common denominator and creating the pathway to our linear equation that leads to the apparent solution at C is equal to 19. Okay, we can check the restrictions again. So 19, okay, this satisfies the restrictions that C cannot be negative or positive 3. So the restrictions are satisfied, and so we have 19 as the solution to number 74. Now, where the restrictions could possibly come in, and we have, let's say in the case of what we have for number 80. Okay, so for what we have in number 80, okay, so you have 4C and we have all over C minus 5. And we have minus 1 over C plus 1. And we have is equal to 3C squared plus 3. And just going ahead and putting the denominator in factored form, so we're going to have C minus 5 and we have times the quantity of C plus 1. Okay, now just some things here. Okay, so we have denominator and factors at C minus 5 and C plus 1. So just for the restricted values, okay, so if C minus 5 cannot be 0, C cannot be 5, and the C plus 1 cannot be 0. Okay, so you have that C cannot be negative 1. And once again, for the least common denominator, okay, we have the quantity of C minus 5 times that of C plus 1. Okay. So we're going to clear out the fractions, just like we're going to do away with C minus 5, C plus 1, as well as the product of the two, just like what we did with C plus and C minus 3, and also packed together. And so applying the least common denominator over these expressions. Okay, so you got C minus 5 times C plus 1 then we have times 4C over C minus 5. Okay, so looking at this first application, okay, so we're going to have C minus 5s are going to go out. So you've got 4C and C plus 1 remaining. Okay, and bringing down the subtraction. And just going ahead and applying c minus 5 times c plus 1 over 1 over c plus 1. And here we're going to have c plus 1 to cancel. Now for what we have on the right, okay, so we have just looking at, so you're just going to have, for the last ratio, you're going to have c minus 5 and c plus 1 to cancel. Okay, so you got c minus 5 times c plus 1. Okay, so we have both c minus 5 and c plus 1. Again, c minus 5 and c plus 1 will completely cancel, so you have 3c squared plus 3 that will remain. Okay, so after canceling out the denominators, okay, so just multiplying the numerator terms, still interacting. So you got 4c and c plus 1. And you got subtraction, and again the quantity of c minus 5. So both c and negative 5 are going to be affected by the subtraction in front. And we have to the right, so we have 3c squared plus 3. Again, 3c squared plus 3. Alright, so looking at distributing, so you have 4c times c plus 1, so this would be 4c squared plus 4c. Now we got subtracting the quantity of c minus 5. We're thinking of like distributing negative 1 over the binomial c minus 5, so we're going to have a negative c. Opposite sign of negative 5 is going to be a plus 5. And that is equal to 3c squared plus 3. Okay. And it looks like we have a quadratic equation in the variable c. And just looking at combining the terms of first degree in the middle. So we have 4c squared plus 4c minus c becomes 3c. And we have plus 5. And we have is equal to 3c squared plus 3. So we now have like terms on opposite sides of the equation. And I can put what I have here into standard form. Okay, so I have 4c squared and 3c squared. And I can move this over. That is the smaller term with 3c squared, so I can subtract, and also I'll take care of the 3. Go ahead and subtract that from both sides. Okay, so I can go ahead and have the right hand side of the equation to be 0. So we have in the rewrite, we have 4c squared minus 3c squared becomes c squared. We have plus 3c, 5 minus 3 is 2. Right hand side becomes 0. And we have with c squared plus 3c plus 2. I can factor. And factors of 2 that will add up to 3. You can see we have c plus 2, c plus 1. Now 2 times 1 is 2, and 2 plus 1 is 3. Now we have entering the phase of applying the zero product property. So I can set each of the factors to 0. So c plus 2 is equal to 0. Now we'll have an apparent solution with negative 2. And with c plus 1 equal to 0, have that c is equal to -1. And so looking at what we have here, trying to verify, now we have for c is equal to -2. Okay, it satisfies the restrictions that c cannot be 5 or -1. So at least this part is satisfied. However, in the case of -1, okay, now -1 does not equal to 5, but with -1, -1 is restricted, for if I put -1 back into c, you have at least a 0 denominator, like 1 over -1 plus 1 is 1 over 0, or the subtraction of 1 over 0, and this last fraction would also have a 0 denominator. And so thanks to this value being restricted, -1 again is disqualified. So what could otherwise have been 2 solutions for c, we have 1 instead. And if -1 had not been restricted from the start, we would have had 2 answers with -2 and -1. But as it stands, okay, we have only that c is equal to -2. All right. Now we'll be looking at a case, okay, that especially it's kind of a difficult problem, but it's one that's kind of designed that sort of stresses how to apply the answers into ALEKS. Okay. And we'll get to this, but I just want to right now I want to get into an introduction with the next category, and this is going to be involving radical equations. And first of all, okay, there is a fundamental, okay, and this is going to be regarded as the principal square root rule. And what this is going to state, okay, is that the square root so you have the square root, okay, and not just with the square root, but also, or any even root. Okay. Now let me just mention, okay, so with square roots, okay, just with notation, so you have square root, you normally see it like this, but it's the same conceptually. If you included what's referred to as the index number, you're looking at second root, okay, and any even root, that's like fourth root, sixth root, eighth root, and so on. Now the square root or any even root of an expression cannot reduce to a negative constant. We'll get into some cases here where the principal square root rule might be addressed. But let me go ahead and say just using a little bit of shorthand like PSR, principal square root rule, does not apply to odd roots. Okay. Odd roots like the cubic root, fifth root, and so on. So the principal square root rule, okay, have concerning directly just the even roots. And let me give you just a little bit of a transition here. Okay, now the principal square root rule, there is, I guess, kind of a kinship between that and the square root property of equality. But these are not the same fundamentals. Now, whenever we had an equation, let's see, back when we looked at the principal, or I should say the square root property of equality, say we have x squared is equal to 36. Let me mention, we had a quadratic equation. So you have with the number 2. Okay, now this equation could have up to possibly 2 solutions. Not always, but potentially. And so on this premise, so you're starting out with the second order equation and with the principal or the transitioning, okay, from x squared to x with the square root property of equality. Again, we had that x is equal to plus or minus the square root of 36 and we have x equal to plus or minus 6 . And so we had x was equal to negative and positive 6. Now, for what we have in the case of radical equations, okay, now if we're looking at solving for x, okay, let's say that if the problem had started out with x is equal to the square root of 36. Okay. All right, so you have x is equal to the square root of 36. And let me just kind of stress the degree here. So you have x to the first is equal to 36. Kind of give you the backdrop to this. Okay, say if the equation is a conditional, which it's going to be, there will be at most one solution. And like this equation was also a conditional where you would have at most the number of solutions being the degree of the variable, which in this case was second degree. Now for x equal to the square root of 36, you have an even root, and the square root of 36 cannot reduce to a negative constant. Okay, so this cannot reduce to negative 6. So just like if you enter 36 and then punch in the square root button, you're going to come out to 6 only. Okay, now in the case of radical equations, now if we have, let's say, in solving for x, okay, if I have that x is equal to the square root of 100 Okay, so again, 100 being a perfect square value. So we have at most one solution, so we're going to have the x is equal to 10. Okay, now let's say that if I change it up a bit and say that I have that the square root of x plus 4 is equal to 7. Okay, so I have the square root of x plus 4 equal to 7. Okay, so I have an even root radical, okay, with the square root, and have the square root of x plus 4. So you have an even root of an expression, and here we have what's going to be reduced to a positive 7. Okay, had this been a negative 7, there would have been no solution. But with the square root of x plus 4 equal to 7, I can solve for x. And so taking care of the radical, so I can eliminate square roots, again, by squaring. In this case, we'll square both sides of the equation. So we have on the left, I have the square root of x plus 4 squared. So this will be x plus 4. And we have 7 squared is going to be 49. And with x plus 4 equal to 49, okay, so we have the x is equal to 45. And you can check 45 plus 4 is 49, and the square root of 49 is equal to 7. And I'll give you some cases here. Let's say that if I have like the square root of 2x plus 5 is equal to negative 3. Again, so I have square root of 2x plus 5, so I have an even root radical, square root. And again, the square roots or even roots of an expression cannot reduce to a negative constant. And guess what? With that negative 3, there's going to be no solution. And it's because of the negative sign. Let's say if I change it up, not with the square root, but a cubic root. And I'll say that I have, in this case, I'll say that I have the cubic root, and let's say that we have let's say we have the cubic root of 2x plus, let's see, oh, here we go. Let's say I had the cubic root of 2x plus 48 is equal to 4. Okay. Again, we don't have to worry about the principal square root rule, because you can have cubic roots of an expression to be positive or negative. Okay, so for the cubic root of 2x plus 48 to the third, okay, that's just going to free up the radical. So the exponent and the radical will eliminate each other. And for 4 to the third, okay, 4 squared is 16. Now 4 cubed is going to be 4 times 4 times 4. So you have, in effect, 16 times 4, which will be 64. And if I isolate the variable term, Okay, so we have upon taking 48 away from both sides, okay, so I have 2x is equal to 16, and we have with division by 2, okay, we're going to have the x is equal to 8. We have also, let's say that if we have the cubic root of x minus 2 is equal to, let's say we have negative 5. So the cubic root of x minus 2 is equal to negative 5. Okay, and again, now if I had the square root of x minus 2 or any other even root and I had it set equal to a negative constant, there would be no solution on the basis of the principal square root rule. But again, the PSR rule does not apply to odd roots. So I can continue. And again, if I liberate the x minus 2 from the radical, so I can cube both sides. Left hand side we have x minus 2. Now for negative 5 raised to the third, we have negative 5 times itself, which will be 25, and then times negative 5, we're going to have a negative 125. And so getting the x by itself, okay, if I add 2 to both ends, okay, so I have the x is equal to negative 123. And that will be the solution here. Okay, and I'll tell you what, just in the case of looking at solving for radicals in the equation, okay, tell you what, and we'll say we have in the group, okay, we'll say we have, first of all, we'll say that x is equal to the square root of 400. And then we'll say we have the square root of 2x minus 4 is equal to 3. And we'll say we have the square root of x plus 2 is equal to negative 10. And we'll say we have that the fifth root of 3x plus 6 is equal to negative 1. Okay, so for the next few moments, okay, if there are any solutions for x among these items, just go ahead and determine those, and we'll discuss in the next few moments. Okay, tell you what, if we go ahead and look into these items, okay, so for number one, we have x is equal to the square root of 400. Okay, now 400 is a perfect square number, and again, we have a conditional statement. X is a first degree, so there's going to be one answer. So while we have two numbers that would square into 400, we have just for x equal to the square root of 400, that's just going to be the positive side of it. And so we're going to have that x is equal to 20. For what we have in the second item, we have the square root of 2x minus 4 is equal to 3. So you have the square root of an expression equal to a positive constant. Okay, that is possible, for it complies with the principal square root rule. And freeing up 2x minus 4 from the square root, again I can square both sides. And for what I have on the left, okay, so undoing the square root by squaring, okay, so you have 2x minus 4, and we have with 3 to the second, 3 squared is 9, and looking at isolating x, where I have 2x for the term, okay, so adding 4 to both ends, so I have 2x is equal to 13. And with division by 2, I could say that we have x is equal to 13 halves. And you can also write this as a decimal, since it does end at 0.5. Okay, so we can say that x is equal to 13 halves or 6.5. And for what we have in the third item, we have the square root of x plus 2 is equal to negative 10. And we got an even root expression, and to try to reduce it to a negative, this would be in violation of the principal square root rule. Again, because the principal square root rule, there is no solution. Now for what we have in case 4, we got the fifth root, 3x plus 6 is equal to negative 1. Okay, so you have an odd root, the principal square root rule does not apply, and you can have odd root expressions to reduce to negatives. So I can proceed. So I can free up 3x plus 6. So we're going to eliminate the fifth root by taking both sides and raising to the 5th degree. So for what we have on the left, okay, so we got 3x plus 6, negative 1 to the 5th. Okay, we have negative 1 times itself, times itself, times itself, times itself, and it's just going to stay at negative 1. And we have with this linear equation, so I have 3x plus 6 equal to negative 1. And upon isolating the variable, we got 3x is equal to negative 7. Whereupon we're going to have x equal to minus 7/3. And there'll be further cases involving radical equations. Okay, now I did want to back up, and I said there was something regarding something I wanted to address with Alex notation. And this is in the case of problem 81. This we have with m over 2m plus 1 plus 1 is equal to 2 over m minus 3. Okay, so we have with our denominators, we have 2m plus 1 and m minus 3, so neither denominator can be 0. So you have like 2m plus 1 cannot be 0. Think of it like if we're trying to solve for m whenever 2m plus 1 is equal to 0, but you cannot have m to be that value. So if we take away 1 from both sides, I have 2m cannot be 1. And so this signals that m cannot be negative 1/2. And we have with the other denominator, we have m minus 3. So if m minus 3 cannot be 0, not only can m not be negative 1/2, it also cannot be equal to 3. And just setting things up for what we have in line, okay, with the least common denominator. Okay, that's just going to be taking the product of 2m plus 1 and m minus 3. And for what we have in this equation, okay, so we've got multiplying the terms by the least common denominator. Okay, so bring down the plus. Okay, this is multiplied by 1 again, and we have for the last combination. Okay, so looking at each of the terms, okay, so for m over 2m plus 1, multiplying by the least common denominator. So we have 2m plus 1 to cancel. So we have situated, we have m times the quantity of m minus 3. And then we have 2m plus 1 times m minus 3. And we're going to FOIL over this. And for what we have to the right, okay, we'll have m minus 3 to cancel. So this leaves us right now with 2 times the quantity of 2m plus 1. And looking at the distributions, okay, so you have m squared minus 3m, and FOILing out this pair of binomials. Okay, so you got 2m times m, so we have 2m squared. Outside 2m times negative 3 is negative 6m. Inside have 1 times m, which is m. Last product we have at negative 3. And for 2 times quantity 2m plus 1, okay, this will become 4m plus 2. And gathering like terms. So we have at the front, so you have m squared plus 2m, and this will make 3m squared. And we have, in the case of first order m terms, we have negative 3m minus 6m is a negative 9m, plus m is going to be a negative 8m. Of course, we have minus 3. Is equal to 4m plus 2. Now we got a quadratic equation in the variable m. And just rewriting this in standard form, that is where we have the equation equal to 0. So I can take 4m away, as well as 2. And gathering the terms. So we have 3m squared. Negative 8m minus 4m becomes negative 12m. Negative 3 minus 2 becomes negative 5. We have is equal to 0. Now we have an equation that consists of a trinomial that we cannot factor into integer coefficients. Okay, you could try 3 times negative 5 factoring by grouping. 3 times negative 5 is negative 15, but there are no combinations of factors that in the integers that will add up to negative 12. You might think of negative 15 and 1 adds up to negative 14. Negative 5 and 3 adds up to negative 2. All right. And for what we have in this case, all right, we're solving for m, and we have as a recourse that we have with the quadratic formula. So we got a is equal to 3, b is equal to negative 12, and we have that c is equal to negative 5, and we have with the quadratic. Okay. Crossing over into the substitution stage, now we got negative b. Now b is a negative value, and I'm going to be taking the opposite sign of this. So we got negative b is the negative of negative 12, and we have plus or minus, okay, the square root, and for b squared, we got the square of negative 12. For minus 4ac, so we got minus 4. A is at 3. We have times c. C is at negative 5. We have all over 2a, so we have 2 times 3. Now for what we have inside the radical, let me just mention, okay, so we have negative 12 squared minus 4 times 3 times negative 5. Now the square of negative 12. Negative 12 times negative 12 is going to be a 144. Negative 4 times 3 is negative 12 in turn. Negative 12 times negative 5 is going to be a positive 60. 144 plus 60 will come out to 204. So right now, negative 12 is going to be a positive 12. We've got plus or minus the square root of 204. And we have over 6. And for 204, this is not a perfect square, but it is one that can be reduced. Highest perfect square that you can take directly into and completely into 204 is going to be only 4. Not 4 times 204, but 51. So you have the square root of 4 times the square root of 51. And so this will be 2 times the square root of 51. Okay, so looking at what we have now, we got 12 plus or minus 2 times the square root of 51 over 6. And for what we have here, now one way that you can reduce okay, notice we have even number coefficients throughout. So if I factor out 2, or 2 halves in this case, 2 will go into 12 6 times. And we have plus or minus. Okay, 2 will go into the square, 2 times the square root of 51, square root of 51 times. And 6 will be 2 times 3. So you can get the 2's to cancel. And consolidated, okay, we have 6 plus or minus the square root of 51 all over 3. And if you leave in terms of Alex, okay, so you have 6 plus the square root of 51 over 3. And we have 6 minus the square root of 51 also over 3. And those would be your answers. But now if you want it in terms of Alex, okay, to get Alex to read this combination, okay, just put parentheses around the numerator terms. If you don't, it'll just take 3 into only the square root of 51. And you want it to also go into 6. Yes.
Why can't you reduce that further? Like,
you can,
take out
but
the
let me
three.
mention this. Let me mention this. Okay, you could. Let me show you this way. You could say you have 6/3. Let's say 6/3 plus or minus the square root of 51 over 3. And this would go to 2 plus or minus the square root of 51 over 3. That is like in case of the other version, okay, we have for Alex. If you do not have parentheses, you can write this as 2 plus the square root of 51 over 3. Notice I do not have the parentheses, so this reads 2 is a standalone term, and 3 is dividing into the square root of 51. And this is another way that you could write this in Alex.